Hello, ladies and gentlemen, and welcome to BJ&Co. This is Odyssey, the next generation science game?
Woo.
Question mark? Did I get it right?
You got it right.
Jesus, shorter title. I'm Savi, your chief engineer of Laughter and Cheer, and I have physicist Ben with me.
Physicist. I love how my
Yeah,
name
sure.
keeps changing. Come on,
I
guys.
know.
Give me one that we can stick with. Throw it down in the comments below.
Yeah, we want a solid one here.
Yeah.
So,
So we'll go from there. I mean, we
hey,
got up to here. We got a book last time. We didn't bother reading it. We think we can figure this out, but we're going to do the right thing and we're going
because,
to read.
we know how much you enjoy reading.
Yeah! As always, timestamps to skip the books are down below if you want to do that instead. But that's lame. Come on, guys. You want to listen to our pretty voices.
Sure.
Today we explored the main part of Wretched Minor across the last rotating
Right,
bridge.
you have better.
We mostly found stuff the army left behind, more shacks and some watchtowers scattered around. There were also a couple more bridges made of steel cables and wooden planks instead of the rotating kind, and they were still in pretty good shape. Mom figured she'd be able to check them out and make them safe in only a couple days with help. The first thing Sid wanted to do was to get the other zipline working to ride down from the bunker to the main part of Wretched Minor. The ziplines were very sturdy and didn't require much repair, so Mum helped him fix that first. Now that we can crank all three rotating bridges, we can make a looping path up to the top of the bunker.
Whoa. So it's still the same sentence.
Yeah, crank the bunker bridge to the zipline we want. Open the top floor bunker door leading to the zipline, ride it down to either side of the island's parts, and then come back across and up again over and over. It was a lot of fun.
You read an extra sentence there, but that's okay.
Whatever.
The watchtowers and shacks were connected with long, color-coded power cables strung all over the island. You'd think they'd be connected in a simple circuit, but the cables zigzag around. Mom thought maybe it had to do with where cables could be buried or hidden best, or some other mysterious army logic. But decades of weather had exposed most of the cables anyway. They looked intact, though. In the shacks, we found some diesel generators, but none of them worked. That's probably why the army left them behind. But Guillaume is good with engines, and he got one running pretty quickly. And he says he thinks he can get them all working again. And there isn't just one key that works with all the generators. Dang it. They all have different keys. Mom's not that interested in generators, though. She brought plenty of solar panel arrays in the boat. They store easily, so we have a lot. The shacks also have more of these army electrical switch boxes, and some were wired into cables themselves. So you have to switch on one to get to the next tower powered up, and so on. Mom said something to Dad about maybe using them to make us more secure in some way. He said he saw no sign of anyone being here on this part of Wretched Minor since the army left, and he seemed relieved about that. But he still liked Mom's idea.
So we're going to move most of our stuff again onto the main part of Wretched Minor. At breakfast this morning, I asked about how Aristotle's physics said the Earth can't be going around the sun. Dad told me two big ways. One, for the sun to rise and set, Earth must rotate. But if it did, then every rock of the Earth would be naturally moving in a circle. And that's what ether does, not Earth. Anything made of Earth only ever moved in a straight line towards the center of the universe, which for Aristotle was also the center of the Earth. Two, that means that Earth is not at the center of the universe now. Then all the Earth would be rushing in a straight line towards it, wherever it was, at a tremendous speed. This would leave behind animals and such which fall slower to float in space, as the Earth zoomed ahead of everything else towards the center. This was because, according to Aristotle, heavier objects, meaning they have more of the element Earth, fall faster towards the center of the universe than lighter objects with less of the element Earth.
The natural speed an object falls is proportional to its mass. So a boulder that's 10 times heavier than a small river stone falls 10 times faster. Wrong. That's why they thought heliocentrism wasn't possible. Aristotle's physics said that earthy objects fall in straight lines towards the center of the universe with speeds proportional to their masses. And they could see this wasn't happening. Wow. And they could see this wasn't happening. There we go. When I drop objects, they do fall down in straight lines, and it makes sense that heavier objects fall faster than lighter ones. So I'm not sure how to prove Aristotle wrong. I'll have to think about it some more. Dad told me not to be so sure that what I think makes sense actually makes sense. God, just out of it. The way to see whether Aristotle's physics has flaws is to do experiments like dropping rocks and seeing how they fall.
It looks like I'll have to make actual measurements, what Dad calls quantitative analysis, where you deal with specific numerical quantities, instead of qualitative analysis, where you deal with how things work generally without numerical measurements. From qualitative standpoint, where what Aristotle says about falling rocks seems right, but maybe it isn't from a quantitative view. Dad suggested I use a visual way of describing and comparing how objects fall using graphs. On a blank sheet of paper, he drew a horizontal line with an arrowhead to the right and said it was an axis that represents time in seconds. He marked the left end point of this axis with a 0 and said that's the instance when we start measuring in our experiments. He drew equally spaced marks along the axis and labeled them 1, 2, 3, and so on to represent every second after that, the start time of 0. He then drew a vertical line out from the start of the horizontal axis at the 0 and said it was an axis that represents distance fallen in meters. The bottom of the vertical axis was already marked 0, called the origin of the graph, and he also made them equally spaced marks upwards and labeled them 1, 2, 3, and so on, saying those represented distance an object falls 1 meter, 2 meters, etc. Whew.
Dad said I could use graphs like this to represent experimental results. If my experiment is dropping a stone off a tower, I draw a starting point on the graph at the origin at the time 0 and also 0 meters fallen because I haven't dropped it yet. Then after I drop it, if the stone hits the ground 5 seconds later and the ground is 50 meters away, I draw another point on the graph at the distance fallen of 50 meters and a time of 5 seconds. If I made any intermediate measurements of distance and time, I would mark them as another point on the graph. It's pretty cool. Here are a few examples I drew for Dad to show I understood. Cool story. I could understand how the results of an experiment, like 10 different observations, could be plotted on a graph as 10 different points, but the graph only showed distance and time. Aristotle said objects fall at a consistent natural speed, and heavier objects had a faster natural falling speed than lighter objects. And that's what I needed to see.
How is Aristotle's idea of natural speed represented on these graphs? Dad said something falling at a constant speed means that over an amount of time, like 1 second, the rock falls the same distance as it does earlier or later over the same amount of time. Like if a rock falls 10 meters in 1 second, then 1 second later it will fall another 10 meters for a total of 20 meters, and a second after that, another 10 meters for a total of 30 meters, and so on. The rock is falling at a constant speed of 10 meters per second. As I was plugging in these points according to Dad's descriptions, I saw that they could all be connected in one straight line. Dad said that the steepness of a straight line on a graph is called a slope. You calculate the slope of a line on a graph by dividing the vertical size of an interval by the horizontal size of the same interval. Like in this example, for an interval of 3 seconds, the rock falls 30 meters, so the slope of the line is 30 divided by 3 is 10. Another way of saying this is 30 meters divided by 3 seconds equals 10 meters per second, and that's the speed of the rock. You can calculate the slope as a total distance divided by the total time, or you can calculate it by taking any smaller section and calculating the distance in that section divided by the length of the time in that section. So the slope formula.
Whoa. Either way, the value of the slope is always the same for a straight line. When you graph distance and time, the slope is the object's speed, and if this line is straight, the speed is constant. And the steeper the slope of the line, the faster the speed, and the sooner a falling object will land. The flatter the slope, the slower the speed, and the longer time it will take to land. That's the end.
No!
Fucker.
Oh my god. One can also make a speed time graph where the vertical axis tracks speed instead of distance fallen. For an object falling at a constant speed, the speed time graph will show a horizontal line. The speed time graph, for my example, would look like this. Since distance is speed multiplied by time, one can get the distance fallen by calculating the area of the rectangle represented by the speed multiplied by the amount of time traveled. In my example, the distance fallen over the first 3 seconds can be calculated like this. 1 second equal the area of the rectangle is equal to 10 times 1 is 10 meters.
Cool story. Fucking Christ. I mean, like, I know this stuff, but...
I'm curious what age this is geared for.
I mean, it's moving pretty quick, to be brutally honest, right?
Yeah.
Like, it's just like, first we had this graph, now we're finding, I mean, and I don't even remember finding area on a graph like this. Like,
Oh,
I
do.
don't.
I do.
Do you?
Yeah.
Okay, well, I mustn't have been paying attention.
That sounds about right.
Yeah. I did well.
You did well. It doesn't mean you were paying attention all the time.
Exactly. Plotting them on a distance time graph, I noticed the graph was identical to distance time graph. What? I started with. Okay, cool. So it's the same fucking graph, bitch. Dad said this was not a coincidence, and I would fully understand why this happened when I later get to study a kind of math called calculus. Half of calculus is called differential calculus and deals with calculating slopes and distance time graphs, and the other half is called integral calculus and deals with calculating areas under speed time graphs.
The two halves are connected in a way that will explain how I got back to the same distance time graph I started with. It's like starting with a number, then squaring it, and then taking the square root to get back to the same number. Getting back to Aristotle, he said that if two stones are dropped and one stone has 10 times more mass than the other, it will fall 10 times faster than the lighter stone, and the lighter stone will take 10 times as long to fall the same distance. It felt like Aristotle was right about heavier things falling faster, but I don't know about them falling that much faster. Now that I understand how to make these graphs, I want to do some experiments dropping rocks off the radio tower to see what the truth is.
Cool story. I mean, they're talking about calculus. Like, that was grade 12. I mean,
yeah,
they're saying you'll one day learn about calculus, but like,
yeah.
All right.
So I'm just going to go ahead and do these.
Yeah.
Because I like math.
I think you got to flip those things. So the things on the, there you go.
Why do I? Oh, so we need to put the right one in the right spot?
Yeah, but I mean, I'll get the 212, like with 330.
Okay, so that's right, because that's 10, and that's what this is. That's 6 over 60. So then we've got 60 over 10, which is 6, which is our 2/12. Right? Okay. Well, I'll figure that out. So then our green is next, which should be the 5. And then this is 3, so we want the 4. And then we want the 3. Right? There we go.
Yeah. Woo.
So much fun. That's done. Woo!
All that reading for something we know how to do.
I'm very curious. Like, I feel like this is like a grade 8 or 9.
Yeah, but I mean, most grade 8 or 9ers be like, it's a fucking game.
Mm-hmm. It's kind of neat to see. Ooh, box. box.
Smash it.
Smash it.
Smash it real good. Okay.
So this says 1 kilogram, 25 degrees. Oh my god.
Okay.
I mean, we're getting into the kind of science I enjoy. So this is nice.
Yeah, but I'm not even getting marked or graded on it.
What, you don't like playing with numbers? Okay, so this one's coming up. It looks like it goes up.
Oh, there's going to be a fucking book. Don't you fucking worry. Wait, what?
No, there's not.
Frick yeah. All right, so now we're doing the, whatever underneath the thing.
So we've got time and distance.
But they also don't have the time marked out. Okay.
Well, I mean, we can extrapolate.
Yes.
Because, I mean, over the same distance, we've got 30 meters per second, 25, 20, 15, and 10.
Mm-hmm.
Right? So if we say 1 second, the area under the graph is going to be 10, 15, 20, 25, 30.
Yeah.
Right? So, what do you think?
No, I don't. I'm just trying to...
So this is purple is going to be, let's say, 30 over 1.
Okay.
Right? So which one of these would be equivalent to 30 over 1?
30 over 1. I mean, I don't know. My brain's not working.
Okay, so it's basically 1, 30. We're looking at the left-hand side to figure out what the actual time and distance
okay.
is.
So 130.
Yeah.
That would be 5150.
Yeah.
Wouldn't it? Yeah.
Yep. So then we just need to flip that up to the top. So then we've got 25 over 1. Or sorry, 125.
125. So whatever that is.
4 and 100. Mm-hmm. Okay, and then we've got 120.
So that's your
480. Yeah. And then 115.
115. 460. So that's right. That's right. So now we got to find speed.
What's the distance over time? So what's 80 divided by 4?
Fucking 20.
You sure?
No, it's not. No, I'm not. Why can't I think? It is 20.
Yeah.
Okay, don't give me this. So that's green then. Throw that one down to green.
Yeah. Okay. So then 60 over 4. 15. So
15. That's the yellow.
Okay. So
we didn't do this the right. We did this fucking ass backwards, but
okay.
So that's 10.
So
there's
that's
your
the
red.
very bottom. Come on.
150 over 5. That's our. Why can't I do that in my head? That's our 30. Yeah.
There we go. So that one's done. I actually like how it's like multiple puzzles.
Yeah, we didn't have to fucking read the novel.
Mm-hmm.
Now we will, because we have no other hints.
Well, we'll see.
Oh, look. Now we'll follow the green.
So, I mean, well, let's follow the yellow first, see where it goes.
Yeah, sorry. I meant yellow. Box, smash it.
I mean, I thought you were bad with numbers, not
I'm just
colors, too.
Been busy. Okay, cool.
30 kilograms, 3 meters. Okay. That's interesting. I wonder if that shows up. Oh, they do show up as different ones. Okay. So these two cut across there, which we can actually get to. And this is the one that we powered. So I feel like
we might as well stick with... Oh, look, a book!
Let's go look. Oh, so right. So right. I mean, I think we do a second book here.
Yeah, fuck
This one seems like it's a little bit quicker than our previous one.
Well, we can hope.
Okay, so by the time we finished dinner and climbed the radio tower, it was too dark to see falling rocks land on the ground at the bottom. We all went up anyway to use the telescope, but we didn't aim it at the sky. We saw a light out to sea, and everyone tried to see what it was, but we couldn't tell. Guillaume said it probably was just another fishing boat. Dad doesn't want anyone to know we're here, so he didn't let us use any lights up there. I had to wait till we got back to the shack to turn on a light and write. Aristotle says if I drop 1 kilogram stone and a 10 kilogram stone at the same time, the lighter stone will take 10 times longer to reach the ground. That seems like way too big a difference. This is really bugging me. If the heavier stone falls that much faster, I wondered what would happen if I took a length of string and tied it to each end of the stone before I dropped them. I tried to imagine it.
Cool story.
Interesting. Okay.
The 10 kilogram stone would fall faster, and the 2 stones would get farther from each other. Oh, okay. A stone to each stone.
Yeah, that makes sense.
And soon the string would get taut. Then the 2 stones would have to fall at the same speed. So maybe the lighter stone would speed up with the heavier stone pulling down on it, and also the heavier stone would slow down with the lighter stone pulling up on it, which means the 2 stones would then fall at the same speed between the speeds they'd fall separately, faster than the lighter stone's natural speed and slower than the heavier stones. But if the stones were falling together at the same speed, it's like they're a single object with the total mass of both stones added together. So 11 kilograms. Wow. And that doesn't make sense. According to Aristotle, an 11 kilogram stone falls faster than a 10 kilogram stone. But if I just figured out that 2 stones tied with a string with the total mass of 11 kilograms would fall slower than a 10 kilogram mass does, but not faster. Both can't be right. I asked Dad about it, and he said I had performed a thought experiment, which is a very helpful way to explore natural laws.
And when the results don't make sense or contradict each other, it usually means some element of the thought experiment was wrong. I wondered if maybe Aristotle's idea that natural falling speed is directly proportional to mass is the part that's wrong. Dad said the only way to prove or disprove this is with actual physical experiments. So now I'm back to wishing it was tomorrow already so I can drop rocks from the radio tower. Mom's grabbed Sid and Guillaume first thing this morning to work on the army cable bridges, but she didn't want me to help because it was too dangerous. My ankles was mostly healed, but it was weak, and she didn't want me to do any work where I needed solid footing and balance. Dad was busy cataloging everything he found on Wretched Miner, which was so far only things the army left behind, so he couldn't help me either. On my own, the top of the radio tower was too tall to see when rocks hit the ground compared to each other, but then I figured it didn't need to drop things from that high. I could start small. I found a kingfisher feather, dark blue with black tip, and thought it would be a great object with lighter mass. Then I looked around till I found a piece of tree branch, a twig really, about the same size as the feather, but a lot heavier.
I held the feather and the twig horizontally and dropped them at the same time. The twig fell a lot faster, but I noticed it fell straight down smoothly while the feather swayed and fluttered around as it fell. So I dropped them both again, but this time I dropped the feather vertically. The feather fell faster vertically than it did horizontally, though still not as fast as the twig. It looks like an object can fall at different speeds depending on its orientation. Oh, that was a good page.
Yeah. It looked like the feather was floating on the air as it fell. When it's horizontal, it must hit more air resistance and fall slower, like how a piece of paper dropped horizontally glides down slowly with so much air hitting it from below. But if I crumpled it, it has less surface area and encounters less air resistance and falls faster. I don't want to deal with situations where air resistance is different, so I'm trying to evaluate Aristotle's claim that an object's natural falling speed depends on its mass, without having to bother about other effects. I need to compare objects of the same size and shape, and then I can know that any speed difference I measure is due to their masses. One of the things I found that the army left behind was a steel ball the size of my fist. Mom thought it might be from a bearing on an artillery cannon, but she wasn't sure. I searched around till I found the right smooth stone, so now I have two spheres that are the same size and shape, but one's a lot heavier.
And instead of climbing the radio tower, I went up to the watchtower instead, since they were shorter. But when I dropped both spheres together, they seemed to hit the ground at the same time. I didn't know how much heavier the steel ball is compared to the stone, but it had to be at least twice as heavy, probably more. According to Aristotle, the lighter object should take at least twice as long to fall the same distance, but I saw no difference at all. I needed a closer look. I went out to where everyone except Dad was working on the cable bridge and asked Sid to drop the spheres off the bridge for me. I waited below. They hit me in the head. I fucking died. Mom says it's about 50 meters high and made a video on my phone of them falling and hitting the ground. I had to watch in slow motion to be sure. The steel ball did land a moment sooner than the rock, but by less than a second. According to Aristotle, when the steel ball hits, the stone shouldn't have even been halfway down yet.
I found Dad in one of the shacks and asked how Aristotle could make such a big mistake. How could he have never noticed something so simple and easy to see? Dad said to repeat the experiment in water, but he wouldn't say why. So I went to the beach. The surf was churning around too much with all the waves, so I got an idea. I went back to the lagoon by the radio tower, closed the door to the cave, turned the swamp pump around, and turned it on. In about an hour or so, I should have a lagoon filled up again with nice still water.
We've read 205 fucking pages.
Yes, we have.
Jesus Christ.
Superstar.
That's just ridiculous.
Just a little bit.
Wow. And we paid money to do this.
Jesus. Aren't we suckers?
That's just silly. Smash the fucking box.
Ooh, another one. 4 kilograms at 30 degrees. 4.6 meters. I feel like we're going to have some fun pendulum swingings.
I mean,
oh, fuck. Are you kidding me?
wow.
It's almost as bad as The Witness.
Okay.
What is this?
Oh, we can turn those things.
Okay. So distance, time taken.
Can we pick those up? Oh no, those are just showing all the things that it can be.
Yeah.
All right, so distance, well, it would be the ball bearing first, then the stone, then the twig.
Oh, fuck, that was right.
That was right.
Done.
Yay.
Fuck.
Get out of here.
That's when I'm close. That's when
Yeah.
I'm not in. How
Really?
annoying is that?
That's weird. Yay, orange.
Follow the orange.
Hey, was there
Next
yellow
cable.
in that one?
What do you mean?
In that last reading we did?
Yeah.
No.
Can't
I
remember
mean,
what it was, but there was.
I was paying attention.
No, you weren't.
No,
I know
I
you
wasn't.
well enough. Jeez, there's a lot of freaking cables.
God damn cables. No fucking book. Shit.
One more?
Okay.
What do you think?
Yeah, fucking let's do it. Let's do it.
Do it! The last one was pretty short. So.
Yeah. And everybody loves reading.
Yeah. I didn't need to fill the lagoon all the way, just up to my shoulders so the water was as deep as I could be without me needing to tread water. The water slowed the spheres enough that I could actually drop them to land gently on my feet and feel exactly when they landed. This time, the steel ball reached my right foot first, and then more than a second later, the stone hit my left foot. The difference wasn't much, but it was more than when I dropped it through air. I thought back to how the feather fell slower than the twig. That must be what's happening here. Air slows down falling objects, and since water is more dense and provides more resistance, it slows them down even more. Then I got an idea. I wasn't sure what was at work here, but if the difference in falling speeds in water is high because water gives a lot of resistance, and if the difference falling in air is lower because air provides less resistance, what would happen if I dropped the spheres where there was no resistance at all? If the resistance was zero, would the difference in falling time also be zero? Unfortunately, there's no way to test this.
I don't have a way to make a chamber with nothing in it, not even air. Well, there is a way if you were smart. You'd make a vacuum. Dad says volume with nothing in it is called a vacuum. Hey, look at that.
You're so smart.
And if I can make one, I can't measure whether the small difference is in landing time. Is the air... Wow, okay. If I can't make one, I can't measure whether the small differences in landing time in the air are entirely from air resistance or whether some of it is because of the difference in mass. Aristotle might be right that mass has some effect on falling times, even if he was wrong about how big the effect is. How can I reduce the effect of air resistance enough to tell if I can't make a vacuum? Thinking about it more this afternoon, something else started bothering me. Aristotle said that the element Earth moved or fell towards the center of the universe at the natural speed. That never changed, but that can't be right either. I can jump off a crate that's only as tall as I am and not get hurt, but I sure wouldn't want to jump off a building or out of an airplane without a parachute. Falling that far means hitting the ground at a higher speed. I could easily show this by dropping a stone over wet ground that's muddy enough to form a crater. When the stone lands, the higher I drop the stone from, the deeper the crater it makes. Or if I drop a stone on a sheet of glass from just a few centimeters, the glass would be fine. But if I drop it from higher, it would break the glass.
It seems pretty clear that the speed objects fall doesn't stay constant. Things go faster the longer they fall. Since water is also a heavy terrestrial element in Aristotle's physics, I decided to see what would happen if I poured water from high up. I climbed a watchtower with a big pail of seawater and poured it out slowly. What I saw was very interesting. The water came out in a steady stream, but the further it fell, the column of water got skinnier, and then broke apart into separate blobs and droplets. Thinking about this carefully, I thought maybe this happened because as the water fell, it went faster and faster.
The water lower down was falling faster than the water above, so the stream as a whole couldn't stay together. It had to break up into blobs as the water below fell faster away towards the ground. It's definitely true that when objects fall, they don't always move at a constant speed. I'm going to ask Dad about it, and also tell him not to worry about any boats nearby. I can see one now from the top of the watchtower, and it looks like an ordinary fishing boat to me. Couldn't find Dad. Maybe he's in one of the shacks on the other side of the island. While I was running around looking for him, I got to thinking about something else. The faster I move through the air, the harder the wind hits my face. Mom's always telling me not to open the car window on the freeway because the wind coming in hits us too hard when we're going fast. So, if the speed of an object increases as it falls, it seems like the air resistance also increases. I also thought about how when I roll the car windows down, the wind pushes on us, but it really throws around Mom's papers in the back seat a lot more. The impact of air resistance might be different on lighter objects than on heavier ones. Then I thought this was maybe what I saw in the lagoon when I dropped the steel ball and the stone through air. They seemed to land at the same time. But when I dropped them in water, the steel ball hit my foot sooner, so it must have fallen faster, because the water resistance slowed the lighter object more than the heavier one.
But it was hard to see what was going on in the lagoon, with the water swirling all around. I needed to do that experiment again under more control to see what's going on. I needed two objects that looked the same, but one was a lot heavier and much lighter than the steel ball or stones for air to have a big effect on them. So I got two styrofoam balls for my art kit and pushed a rock into the center of one to make it a lot heavier. Then I got a fan, one we were using to cool off the room we slept in at night, and I put it on the floor facing up. When I dropped both styrofoam balls over the fan, when it was off, they both landed on it at about the same time. But when I turned the fan on high, blasting air up, and dropped them again, the heavy ball definitely landed first and the lighter ball after that. The only change I made was making the air hit the falling balls harder, and this definitely slowed the lighter ball down more than it did the heavier ball.
So it makes sense that heavier objects fall faster than lighter ones, because the air resistance slows down lighter objects more. But is that the only reason there's a difference? Or are there other things also causing some of it? For instance, Aristotle's theory that objects of more mass fall faster just because they have more mass, then there would still be a difference even in a vacuum, where there was no resistance. I can't think of a way to test this since I can't change the amount of air there is around my falling objects. It occurred to me that if I can't reduce air resistance by removing air, I could reduce it by having the objects move slower. When I roll down the window in Mom's car, the wind hits us hard on the freeway. But pulling into the driveway slowly, I can hardly feel the air at all. If I just keep things going slower, I'll see less interference from the air. But I can't change how fast things fall. If I drop objects from a table instead of a watchtower, they wouldn't fall as far, so they wouldn't speed up as much, and then would minimize the effect of air resistance, but the objects wouldn't fall for very long, so it would be hard to measure any differences in their landing time. I told Dad about this and how I was stuck. He said I could use a pendulum. I thought that was a weird idea.
I'm trying to test how objects fall straight down, but the swinging weight of a pendulum moves in a circular arc. Dad said I could think of a pendulum as a way to slow down vertically falling motion and minimize air resistance effects, since the ball would take more time to fall and not speed up as much. Also, a pendulum would let me do experiments with an object falling a long distance without speeding up faster and faster, because the weight of the pendulum, called the bob, rises and falls over and over, speeding up but then slowing down again. So I could have a continuous series of short falls where any differences in falling times would get amplified after many swings. I asked Dad how a pendulum could be a continuous series of falls when half the time the bob was rising. I also asked whether the string interfered with motion since the bob wasn't falling freely. Wouldn't the string speed up or slow down the bob? If it did, that would mess things up. In free fall, nothing but air touches and pulls on the objects falling. Dad told me I should use symmetry to answer the question about whether a pendulum going up or down was the same as something only falling down.
Wow. And he said I should separately test whether the string adds or subtracts to the speed of the bob. I'm not sure how to do either. I'll think about it more after dinner. It wasn't clear to me how the entire motion of the pendulum could be called free fall when half the motion was the bob rising, not falling. I tried to use symmetry to figure it out like Dad suggested. With the pendulum, I imagine the bob swinging back and forth. At the moment when the bob is straight down, it's moving sideways at some speed. I'll call that speed v. Then the bob swings up at the moment when it stops and is about to swing down again. It's some distance higher than when it was straight down. I'll call that height h. When it falls at the moment it's straight down again, it must be going sideways the other direction now at the speed v again. I know this because of symmetry. When a pendulum swings back and forth, it rises to the same height on both sides of its swing. So if speed v to the right makes it swing up to height h, When it reverses directions and swings up to the height h again, it must also have been going speed v to the left when it was straight down. Holy fucking Jesus.
The swinging gets a little less and less over time, of course. Mum says this is called dampening. It's probably because of air resistance, but in the first few swings, any difference isn't noticeable, so I can ignore it. This means pendulum motion from the left side down to the vertical position and the motion from the vertical position up to the right side were two sides of the same coin. The falling and rising of a pendulum can be analyzed as if it fell 2 times in succession, from rest through height h to final speed v. A sequence of oscillations could then thus be analyzed and treated as if the bob is falling many times back to back in rapid succession, from rest through height h to speed v. This analysis was convenient for me because the final speed v at the end of any individual fall event was always low, so I could ignore air resistance effects on the pendulum until they accumulated after several seconds. That's assuming the string isn't changing anything. I need to think about that next. I need to test whether the string of a pendulum adds or subtracts to the falling motion of the bob, other than changing its direction. To do that, I had to compare what happens with different string lengths to what happens with the same object falls freely without a string. If all the pendulum does is lengthen the falling time, then the speed at the bottom of the swing, after falling vertical height h, should be the same whether it's falling down or swinging sideways.
But how could I measure the speeds to check that they are the same in all cases? Dad suggested I make a pendulum by hanging a bob and string from a nail, a pivot, on a piece of plywood. That way I could make marks on the wood for how the bob was swinging. When I did, I held the bob up, made a mark next to it on the wood with a pencil, and then dropped it, and also made a mark on the other side where the bob was highest before falling down again. The marks were, of course, at the same height because the speed of the bob at the bottom of the swing was the same in both directions. Then Dad said for me to put a second nail directly below the pivot where the string was tied, about halfway down the length of the string. I did it and saw what Dad was doing. When the bob swung down and the string hit the nail, only the lower part of the string swung up. And it was like at the moment the length of the pendulum string got shorter by half for the swing up, but when I made a mark at the high point it swung to, then it was still the same height as before. I moved the nails to a lot of different points, and it didn't matter where I put it. The bob always swung up to the same height when I dropped it, just following a different trajectory.
Well, that's handy. If I didn't put the nail too far down, of course. Except for that, it didn't matter how long the string of the pendulum became. The bob always swung up to the same height it swung down from. And if the height the bob rose didn't change when the length of the pendulum changed, that meant the speed it was going at the bottom of the swing doesn't change either. No matter how long the pendulum was, the bob could always rise to the same height and fall back with the same speed v. But how could I be sure that using a pendulum wasn't making the speed at the bottom of the swing different compared to an object falling freely without a string at all? I got an idea. In my art supplies was an old toy gun that shot ping pong balls with a spring. The barrel of the gun was not a closed cylinder, but open on top like a trough, with a spring and a trigger to release it. I attached the ping pong ball to the string and made it to make it the bob of a pendulum. And then I cocked the gun, held it next to the board directly below the pivot with the string hanging straight down, and then I pulled the trigger. The spring hit the ball and gave it initial speed to the right, and I marked how high the ball swung up on the plywood before swinging down again. Then I detached the string, put the ball in the gun, and cocked it. If a pendulum doesn't change speed compared to falling freely, then I should be able to shoot the ball straight up from the same spot as before when it was a pendulum bob, and it should go up to the same height as it did on the pendulum before falling again.
And it did! So, by symmetry, it is clear that when a ball falls a height h, whether vertically or along the curved path of the pendulum arc, its speed at the bottom is the same. Pendulum does not change the final speed of a falling object. It just makes the object fall along a longer curved path. So, it takes more time to attain that speed. A fishing boat came this afternoon. We heard the motor coming before it got here, and I figured we'd just go out and meet them to tell them we had permission to be here. But they didn't, and had to leave. But that's not what happened. Mom and Dad told Sid and me to stay in the shack. They didn't want anyone on the boat to know we were here. Then Dad took Guillaume to the dock As soon as they left, Mom cranked the bridge away so no one could get to us. Bang!
Oh, shit's going down.
They're all dead.
Good thing she brought a gun with her.
Jeez,
I wanted to watch what was happening, but Mom kept us out of sight. Dad and Guillaume were gone for about an hour, but it seemed like a lot longer. Then we heard Dad call us, and we went outside and cranked the bridges back for them to cross over. Dad said it was a fishing boat, but it didn't look like they had done much fishing lately. It was good we had Guillaume, because the sailors only spoke French, which Guillaume knows, so he translated. The sailors knew it was illegal to come to the island and wondered what we were doing here, and Dad explained the best he could through Guillaume. But they didn't dock just because they were curious about why we were here. Their radio was broken, and they asked if we could use ours to tell their friends they'd meet them at their fishing spot a day late. And Dad let them use the one on our boat. They asked if we had a satellite phone too, and Dad said no, even though we do. Then the sailors wanted to look around, but Dad told them they needed to go. He said it got a bit tense, and then the sailors nodded and left, waving goodbye. Guillaume said he thinks they were just wanting to get invited to a better meal than they had on their boat. Dad said he hoped that was all it was. I thought maybe seeing the sailors would make Dad less worried now that he knows who's out there, but he seems more worried than before.
Oh, thank God.
Thank God.
Fuck.
Okay.
Alright, pendulum. Cool.
What can we hit here? Interesting.
This is quite the device that she's built.
Yeah.
Oh my God. Look at it. It's the same fucking height, man. Oh my God, it's the same height. Okay, cool.
But do we need this to power something? No.
Okay.
Fuck. Because that's already powered. I mean, this does this.
Alright, well, this is your ping pong ball thing.
It's kind of neat to see what they built into this.
Mm-hmm.
And now they hit at the same time. Plop. Yeah. Okay.
Yay. Okay, cool.
So I figure I figure we see where this goes and then we head out because fuck, there's wires all over the place.
Yeah. Gonna have to do a lot more reading. Hit the fucking box!
BAM! I mean, I think this is the
only-
last one of these.
It's the only thing that's keeping me going is hitting boxes.
Wow.
Yeah.
Oh no, there's still one more
Missing
coming.
one.
Still one more coming. Go, 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 go. So many cables.
Ben has just remembered he can run.
Shush. Ah!
No, frick. That'd be a little excitement to this video, if you know what I mean.
Oh, that goes through a cave. Oh, pink wire. I can't touch that, sorry.
Wow. Okay.
Okay, this is doable. What, I don't know what we can move.
I don't know what we're moving, but...
1, 2, 3. So this starts at there, so this is going to be whatever's on 2. So this one here is at the bottom, so it's going to be whatever goes back to the bottom. This one here is, what, third from the top, so it's going to have to be this one.
Okay. I was just like, what's going on here? Alright, so this needs to be the top one.
Yeah,
Right, there we go.
Where does the
Nailed.
pendulum going to end?
Right.
Okay,
Yep. Well, that was the thing.
that was the thing.
Woo. Yeah. These puzzles are getting challenging.
I
Except
mean,
not really.
to you,
No, I was not with it right now.
I can tell.
Okay, cool. Oh, Ben's going secret path, hidden way. Oh my god.
Just go back that way, I think. I don't know. Yeah. I'm curious. I'm such a completionist that it's like, ooh, maybe there's a hidden collectible here.
Let me tell you, we want to finish this as fast as possible,
so we can get on to better playthroughs. I feel like we got a room 2 coming.
Room 2, yeah, for sure.
And the witness. We gotta finish the witness.
Witness, yeah.
Almost
which
done there.
Should be a couple more episodes. Fuck that.
I'm gonna open it and take it, and then we're gonna go out because then it'll save the game. Hopefully. Hey! So that is it for this week's episode of Odyssey, the Next Generation Science Game. Had some fun physics-related puzzles, which is kind of nice. So it's always enjoyable. So thank you guys very much for joining us on the journey. As always, if you enjoy this, don't forget to smash that like button and subscribe to the channel for updates when all of our new content goes live. Savi, it's been a pleasure working with you, having somebody to share the reading with me.
Just welcome to BJ&Co read along.
Read along. New weekly series. We'll just read to you.
Nope.
You love our voices so much.
Nope.
Okay, thanks for watching, guys. We'll see you all next time.
Bye.
Bye.